Good afternoon, I'm Mr. Ish. Thank you for joining me for this volume exercise video. We have a bunch of equations over there: y equals x cubed, y equals 0, x equals 1, and then we have 4 lines of axis mentioned over there, or lines of rotation or revolution: x-axis, y-axis, x equals 1, y equals 1. We're going to be doing the determination of the region bound by these, and then we will sequentially do the rotation or revolution around each of those lines of axis. We'll start with the x-axis first. Our equation over here, y equals x cubed bound by y equals 0 and x equals 1, would look very much like this, and I'm only showing you the part which will be demonstrated by these three. Y equals 0 is your x-axis, x equals 1 is this, and here's your y equals x cubed, and you know I would continue on right here. The region bound by these three lines is all of that, and we're doing a rotation here around the x-axis, and you know you're going to generate a good rotational solid. The rotational solid would look something like this, a closed through and through solid, but it would look like that. Anyhow, the determination of the radius in here is not hard by any means. You're looking here again at a curve which looks like this. Any point from your x-axis up to this curve is your radius, and here the radius is x cubed. All the cross sections over here are all circular, as you're seeing right here, circular cross section, which will feed through the pi r square for the area of that slice. And you know pi r square with radius x cubed will be pi x to the 6th. This will be integrated from your lower limit is 0 to your upper limit. What is that? That's going to be this. Because you're looking at everything from right here up to right over here. From 0 up to 1. You have a horizontal line of axis or horizontal line of rotation. Therefore, you must have an interval based on the x-axis 0 to 1. If you don't know that, all you have to do is just make your equations equal to each other, or this one right here and this one right here, and solve, and you'll easily get 0 comma 0, and you'll get 1 comma 1 and 1 comma 0. These will be all your points. Here's 0 comma 0, 1 comma 0, 1 comma 1 right over here. Anyhow, we have x to the 6th dx. You'll integrate this for the volume of that solid, rotational solid. It'll be x to the 7 over 7, upper limit 1, 0, and you have a pi sitting outside, and your here volume will be pi over 7. So we'll write this here as pi over 7. The volume of this solid, the volume of the solid obtained by this bunch of curves through that line of rotation x-axis is pi over 7. Alright, now our next line of rotation or line of revolution is y-axis, and we have exactly the same representation here. The region bound by this bunch of curves, x-axis, x equals 1, and your y equals x cubed. But here our rotational movement, or you will say now the revolutionary movement, well actually it will be a rotational movement, will be the y-axis. And your solid would look something like this. Like that. All of that, and then you'll have this, and you'll of course have a three-dimensional effect. It's a rotational solid because this point right over here will always stay firmly fixed, which is this 0 comma 0 intercept of this region. It'll always stay firmly put. You'll have an open bowl-shaped solid, closed on the periphery, but it's open as a bowl-like shape on the inside. Of course, when you do a cross-section of this and you bring it out, what are you looking at? You're looking at a washer developing, right, in terms of a cross-sectional slice. Therefore, now you must worry about inner and outer radii, because this right over here is my y-axis around which this rotation is occurring. From here to right here is my inner radius. From here to the outer edge is my outer radius. All of this has to be determined, but all of this is easy. You have a vertical line of axis, therefore equations must be presented, or this equation must be presented in the x equals format, which is x equals y to the 1 over 3, or cube root y. That right there is your equation. Interval will be along the y-axis from 0 up to 1. Again, 0 and 1 in this direction, 0 to 1. Because of the nature of these curves, you don't lose these points. The intervals will always stay the same. Anyhow, and here right will be my 1 comma 1. That right there will alone tell you your intervals along the x-axis and intervals along the y-axis, or a horizontal line of rotation or a vertical line of rotation. Now the inner radius will be from your y-axis to the first curve, which is right here, and then your outer radius is from that to the next curve, which is your x equals 1. So the inner radius here is from your y-axis to this y to the 1 over 3, which is just y to the 1 over 3. Outer radius is just up to 0 to 1, which is just 1, and then inner area is this square, which is pi y to the 2 over 3. Outer area over here is of course pi. Volume is always here with regards to outer area minus inner area, and we can isolate the pi's and bring them out. Again, from 0 to 1, we have 1 minus y to the 2 over 3 dy. Integrate this polynomial. It's not hard by any means. You'll get a y minus from here. What will you get? You'll have n plus 1 divided by n plus 1, 2 over 3 plus 1 divided by 2 over 3 plus 1, which is what? It's going to be y to the 5 over 3 or 5 over 3. From 1 to 0, you're basically just looking at pi and then 1 minus 3 over 5, because this will flip around. 1 minus 3 over 5 is easily a 2 over 5 pi, and that right there is going to be your rotational solid volume of this. Let's put it over here. 2 pi over 5 is that volume. These are my volume results right over here, which we'll put down. Let's look at this along the x-axis. Let's draw everything again. Here's my x cubed, x equals 1 and y equals 0. My region of space bound by those three equations is this right here. My line of rotation is x equals 1, which is right here, x equals 1. You'll again develop a rotational solid. So these will be all rotational solids. We will have something which will look like this in terms of a solid right over here. And it'll look like this. That'll be our solid. But in terms of the radius determination, it's not hard by any means. Everything is being determined always from your line of rotation or line of axis. Here it's x equals 1. All you have to do, well, we can draw it out here again. Here's my x equals 1 and we have a curve like this. All you have to do is look in this direction. And you have only a single radius to determine. The cross section over here is very easily just a disk. There's no washer being developed over here. What is your radius here? It's going to be determined from your line of rotation, which is 1 minus the distance up to that, which of course has to be in the x equals format because you have a vertical line of rotation, which will be y to the 1 over 3. And then the area of course is pi times 1 minus y to the 1 over 3 square, right? And that's pi. And then you have 1 plus y to the 2 over 3 minus, now you got to do the intermediate term over here, 2y to the 1 over 3. You have to integrate this. Integrating this is not hard. It's all polynomials. So let's do it. You're going to do volume integration here with the pi pushed outside, always again from 0 to 1. Because again, all of these points are 0, 1 and 1 comma 1. Everything works out very well with that regard. We'll have a 1 plus y to the 2 over 3 minus 2y to the 1 over 3 dy. Remember, when you have vertical lines of rotation, you'll end up with a dy. When you have horizontal lines of rotation, you have dx, and everything accordingly changes. You'll have a pi over here, you'll have a y plus y. 2 over 3 plus 1 divided by 2 over 3 plus 1 is a 5 over 3 or 5 over 3 minus 2y, and then 4 over 3 and 4 over 3. And all from 1 and a 0. What we need to do is generate some space so we can finish this, and it's not hard by any means. We'll bring it all over here. You have a 1 coming in and a 0 coming in. 0 is meaningless. All of these denominators will flip around. You'll have a 1 over here plus 3 over 5 minus, well, 2 times 3 over 4 will be a 6 over 4, which is a 3 over 2. That's exactly what you're having. You can do this arithmetic on the side, and I'm pretty sure I'm not making a mistake here. You can do a common denominator here of being a 10. You'll have 1 going in 10 times, plus 5 goes in 10 2 times, 6 minus 2 goes in 10 5 times, 15. And then when you do this 10 plus 6, 16 minus 15 is a pi over 10. And that's the volume of this solid, which is generated over the x equals 1 line. And it looks right to me. Our last one is this, y equals 1. It shouldn't be too hard. Again, we have all of this region bound by these lines. X equals 1, y equals 0, and y equals x cubed. Here's my rotational line, y equals 1. And we're doing a rotation around it. Again, it'll be still a rotational solid, and it's going to be an interesting one. And let's show it to you what it would look like. Here's my rotation. And of course, I'm not drawing anything to scale over here, but I can try to draw things to scale, but what's the point? We're just trying to do a good effect over here of what everything will turn out to be. And it looks something like this. Here's my horizontally directed bowl, a rotational solid, because this point here will always stay fixed as it rotates around that y equals 1 line, and you'll never move out of place. There's no sense of a revolution occurring here. Everything is rotation, so it's a rotational solid. But anyhow, we have a cross section over here which will determine, and it'll determine basically our path forward, and it's a washer we're seeing over here. Very clearly a washer. Here's my y equals 1 line around which the rotation is occurring. Everything has to be measured with regards to inner and outer radii from that line. Remember, when you have a washer cross section, you're thinking about inner and outer radii. when you have a disk cross-section or cross-sectional slice, you're only thinking about a single radius. From my y equals 1 line, if you look down at the first curve, that's your inner radius. Then from that same line, if you look to the very next curve, which is your x-axis, that's your outer radius, and that's not hard. Inner radius here is going to be generated from 1, and you're going to the first curve, which is x cubed. Remember, horizontal lines of axis, horizontal lines of rotation or revolution, everything is y equals x format. Dx with regards to integration and intervals along the horizontal dimension, which is 0 to 1. Here's my inner radius. My outer radius is just from 1 going up to this x-axis, which is y equals 0, which is just a 1. This right here is 1 minus x cubed. But you gotta run everything here through the circle formula in terms of area pi r square. This right here will be 1 minus x cubed whole square pi. That's my inner area. And my outer area will be pi. We have to calculate this inner area. It's going to be a good polynomial which will generate 1 minus 2x cubed plus x to the 6th pi. And here, you know, we still have a pi. So we have to now actually do the calculation over here. And let's do the calculation. I have the outer area which I'm bringing right over here, and I'm erasing it from here so I can do my entire integration here on the bottom. Volume will be with the pi pushed outside from 0 to 1. Outer area, which is 1. Remember, pi has 1 coefficient minus all of this. 1 minus 2x cubed plus x to the 6 dx. But I want to conserving space where these ones will cancel out. I will really be looking at a 2x cubed minus x to the 6 minus x to the 6 dx, because that's how the algebra played it out to be this way. Now let's do the definite integration part. 2x cubed will come out as a 2x to the 4 over 4 minus x to the 7 over 7, upper limit 1 and 0. But this 2 over 4 can very well simplify to an x over 2, and you know you can do that. But with regards to these values we have over here, everything is just basically pi. We have a 1 over 2 minus 1 over 7. These to the powers of 4 and 7 are meaningless in the face of this 1. What's 1 over 2 minus 1 over 7? Well, we can get a good denominator here of a 14. And what will we get? We'll get 7 minus 2 over 14, which is what? A 5 pi over a 14, and that'll be the volume over here. So the volume of this solid specifically will be 5 pi over 14. All of these have been demonstrated here for you, and they're worked out. All of those are right and correct. I believe I don't have any mistake here on the board. But we've seen this exercise through to completion, utilizing the same framework but across 4 different lines of rotation. All of these were generated rotational solids. There was no other effect here other than a pure rotation occurring, but from a different line of axis. Thank you for watching. Stay tuned. Have a nice day.